We're going to be looking at relations and functions. So a relation is a set of pairs of input and output values, and there's 4 ways to represent this. So I will either have an ordered pair, which you should be familiar with. It's an ordered pair x and y, where x is your input, y is your output. Mapping diagram, so a mapping diagram will look something like this, where we have numbers being mapped to each other from our domain and our range. We have a table of values, which is like a t-chart, x and y. And then we have a graph, so when we have our x and y axis and we actually go ahead and graph those values. So here's an example of ordered pairs. So I have an x and y value. So here I have a relation listed. -3 is paired with 4. The input value here is 3. The output value here is -1, 4, -1, 4, and 3. And here I have those same values, but now in a mapping diagram. So I have my input and my output values, my domain and my range. And the arrows show how to pair each of the values together. So -3 went with 4 here, so -3 has an arrow to 4 over here. Here I have a table of values, or a t-chart, where we have our x values and our y values, and those are written in columns, and then the rows are the ordered pairs that go together. And then here's the graphical representation where we're actually plotting them on an x and y coordinate plane. So the domain of relation is the set of the input values, or just the x coordinates, and the range is the set of the output values, or the y coordinates of those ordered pairs. So here I have a set, this is a relation, and I have all the ordered pairs that are in that relation, and I want to write the domain and range for this relation. So the domain is going to be just the x values. So the domain is just going to be the x values, and I want to write those in ascending order. We're going to use set notation, so I have an open bracket, and then we're going to write them from smallest to largest. So smallest here is -3, and then it looks like we're going to have 0, 2, 9, and 23. Close the bracket. And now the range is going to be all the y values, and again we're going to write those in smallest to largest. So it looks like -99, -18, 0, 7, and 14. And if any of these values were to be duplicated, so let's say that -3 appeared more than once in the x coordinates, I would not write it more than once in my set notation. I'd only write it once. So we have this idea of a function. So anytime you have a relation, it has the possibility of being a function. So a function's a well-behaved relation. Every element in the domain will correspond to only one element in the range. Okay, so every x can go with only one y in order to be a function. The same x value cannot go to more than one y value. So let's say our domain, our x values, are being represented by a girl wanting to go to prom, and our range is a gentleman who is going to take that girl to prom. So for a function, we're going to have one girl going with one guy. So every girl is only allowed to have one date. Now, that is not to say that every guy in the range can't have more than one girl. So over here, this is a function because every girl is only going with one guy. Every x is paired with only one y value. Now over here on the right, you can see that the lady in red actually has 2 dates. So this is not going to be a function. Okay, so the relation on the left here is a function and the relation on the right is not. So please make sure that you do not confuse the y values being paired with more than one x. That's okay. It's just for every x, only one y. So let's look at some of these relations and see if they are functions. So for this first one, this mapping diagram, I have -3 going to -2, 0 going to 7, and 4 going to 1. Notice how the arrows here, I only have one arrow coming out of each x value in the domain. So every x is going to only one y. So yes, this is going to be a function. Now down here I have ordered pairs. So first let's look at the domain. We have 4, 8, 1, 6, and 4 again. Notice how 4 is repeated twice, which means 4 is being mapped to 1 and 4 is being mapped to -1. So that x value has more than one y value, so no, this is not going to be a function. If I'm given a graph of a relation, I can figure out if it's going to be a function by performing the vertical line test. So the vertical line test simply says that I look at the graph and I either actually draw vertical lines or I visually imagine placing my pencil on the paper and creating these vertical lines and seeing if this vertical line hits 2 or more points on the graph. If it does, then it is not going to be a function, and if it does not, if it only hits once, then it is a function. So here you can see I'm performing the vertical line test, and it hits this graph twice. Therefore, this is not a function, okay? So a girl has 2 dates to prom. This x value has y1 and y2 as a date. So a girl is going to prom with 2 different dates, which is not allowed to be a function. So performing the vertical line test, we can decide, is the relation we have only a relation or is it a function? So remember, functions are special types of relations. So here, doing my vertical line test, you can see that I'm going to cross over and pass through 2 points when I draw my vertical line, so this is only a relation. Here, drawing my vertical lines, I only ever hit one value, so this is a function. Here, I will only ever hit one value as well, so this is also a function. This V graph here, I only ever hit one value, so this is a function. And here immediately you can see that I'm going to hit 2 points. It doesn't matter where I draw the line, so this is only a relation. A function rule tells me if I have a particular x value, how do I find the y value that goes with that x value? So there's a few ways to represent functions. We have function notation as well as the normal y equals notation that you are used to. So y equals 3x plus 2 is one way to represent a line. We have our input and our output values, our domain and our range values. But I could also replace that y equals with f of x equals, and I did not change anything. It's still the same function. So we say this f of x or function f of x, and this allows me to use this notation in a variety of other ways than I could before when I only had y. Because when I only have y, I can only talk about one function at a time. When I have f of x, I can talk about more than one function. If I'm talking about multiple functions, I can use different variables. So I can have g of x, I could have h of x, and I could be using all of those simultaneously, but still assigning each of them only one function rule. Now when you see this type of notation here, like f of 1, that simply means plug in 1 everywhere you see an x in my function. I want the input to be 1, and finding f of 1 is finding the output or the y value that goes with x equals 1. X is always our independent variable and y is always our dependent variable. Now remember, we are also calling y f of x now, but these two mean exactly the same thing. Now why is f of x our dependent variable? It's because it depends on x. So we have to plug in x, do our function rule, and then get out a y or an f of x value. So what we get for f of x depends on what x we plug in. So we always have a cause and effect. Our x, our independent variable, is our cause, and our effect is our y or our f of x coordinate. For this problem, I want to evaluate the function at -3, 0, and 1/4. So I want to find f of -3, f of 0, and f of 1/4. Remember, this simply means plug in -3 where I see an x, plug in 0 where I see an x, and plug in 1/4 where I see an x. So let's go ahead and evaluate that and find our output. So I've gone ahead and plugged in all of our input values to get our output values, and once you're done you can write those as a coordinate pair. So when I input -3, I get 11. So my x value is -3, my y value is 11, and so forth for the other coordinates. So one way to describe the dependence of a variable is saying a phrase such as distance is a function of time. So we're saying that distance is dependent on time. So that means my distance here would be the y value because it is the dependent value. And then time would be the x value because it is independent of the distance. So tickets to a concert are available online for $35 plus a one-time handling fee of $2.50. The total cost is a function of the number of tickets bought. So cost is a function of the number of tickets. The cost is dependent upon how many tickets you buy. What function rule models the cost of the concert tickets? So in the problem it says cost is a function of the number of tickets. So our cost is going to depend on the number of tickets we sell. So our cost is going to be our dependent, our f of x, and our independent is going to be the tickets, which is our x values. So the function rule here, the cost is depending on the number of tickets. Well, it's $35 a ticket plus this $2.50 fee. So notice how I will input values for the number of tickets, and then our output value will be the cost. So the cost depends on how many tickets you plug in. So if I want to find 4 tickets, that's f of 4, and I plug in 4 where I see an x. So I'm going to get f of 4. So for 4 tickets, I'm going to spend $142.50. Alright, give these problems a try. Make sure you include all your work in your notes. So give these a try. Tell me if these are relations or functions.